Hello guys and welcome back to the Physics and Maths blog. Today we're going to go over another video in our Abstract Algebra series. Today is the third video and we're on complex numbers. So complex number, the set was mentioned in the first video, but now we're going to explain them a bit more. So real or complex? What is a complex number? Well, we know that a real number can be visualized geometrically as a point on a line, usually on the x-axis. We can take this knowledge of our x-axis and we can, instead of having an xy plane, we can have an xi plane, which is kind of different, where instead of two real numbers, we have this real and this imaginary number. So, like I've written here, a complex number can be regarded as a point in the Euclidean plane, as shown in the figure to the right, but instead of the usual y-axis, we have this i-axis, which is the imaginary number. And instead of a coordinate sort of brackets, we have a and b or whatever, we now denote this coordinate as a plus bi, where a being our real value on the x-axis and b is our imaginary value on the y-axis. So what is I? Why do we have this imaginary axis? So the complex number I was invented to provide a solution to the quadratic equation x squared equals minus 1. So that requires that I squared equals minus 1. Essentially I was made to figure out it actually can be useful in a lot of complex stuff, but we just learn it at this level because then we can apply it and get a lot more better understanding of how the world works. So this I has been called the imaginary number, which can lead to some confusion, but the best way to think about it is that it's the square root of minus 1. And then just think about it as the square root of minus 1, don't think of it as I, because then in your questions you can use it as I, and then when you square out something you just get minus 1, so it becomes quite a nice number to deal with. So we did mention the set of complex numbers before, so now this set of complex numbers is defined by this integral where a plus bi, where a and b are both reals, and bi becomes an imaginary number due to the I value there. So it takes the real number b and takes the imaginary number I and then becomes a complex number. So what if we want to multiply complex numbers together? Well, we have this product, let's say a plus bi times by c plus di. It's defined in a similar way to what we previously know about multiplication, but we just need to apply our knowledge that I squared equals minus 1. So we see the following, that a plus bi times c plus di gives us this value, ac plus ADI plus BCI plus BDI squared. Now applying that, we know that I squared equals minus 1. We can plug that in and we can sort of simplify it to get AC minus BD plus, in brackets, AD plus BCI. So that gives us a new complex number. So I'll pause this video, try and compute this complex number multiplication. So 2 minus 5i and 8 plus 3i. Pause it, have a go and come back and we'll go over the answer. So the answer you should have got is 31 minus 34i. So we've got 2 times 8 is 16, 2 times 3i gives you 6i, minus 5 times 8 that gives you minus 40i, and then minus 3i plus 3i gives you minus 15i squared, but our I squared becomes minus 1, and so you get plus 15, giving you 31 minus 34i. So graphing complex numbers or polar coordinates. So if we want to establish a geometric meaning to complex multiplication, we can define the absolute value of this a plus bi to be the square root of them both squared and square. So what you do for Pythagoras is theorem. So this gives you sort of the length from the origin, distance from to a and b, this point on this imaginary plane. So this will allow us to describe the complex number, whichever one we have, in polar coordinate form. So our z is equal to this absolute value of the complex number times cos of the angle plus I, imaginary number, that is, sine of the angle, where the angle called the argument is the measurement counterclockwise from the x-axis to the vector. So as you can see in the diagram below, we have this point here, this point P, and we have our argument measured from the x-axis, and our z point is minus 2 plus 2 square root 3i. So if we square both sides of them and add the square root them, then we can get the distance, and also we can get the angle, which is the argument. Thank you guys for watching. I hope this made sense. Sorry if it was a bit hard to understand. There's a video following up with some questions about complex numbers which will help with your understanding of it. Thank you guys for watching. I'll see you guys in the next video. Goodbye.